Hello students, in this video we have 6 illustration of chapter 6. The question is, a metallic rod of 1 meter length is rotated with a frequency of 50 revolutions per second with one end hinged at the center and the other end at circumference of a circular metallic ring, radius 1 meter about its axis passing through the center and perpendicular to the plane of ring as shown in figure 6.6. Constant and uniform magnetic field of 1 Tesla is applied parallel to the axis uh, and it is present throughout its length. And what is the EMF between center and the metallic ring? Let us try to understand situation. Before we go to that, uh, let me remind you of the motional EMF. We will need that topic here. Consider a region of uniform magnetic field. The crosses are indicating that outside the screen we have north pole, inside we have south pole of magnet, and hence magnetic field lines are going inside. Okay, and what will happen if I take a metallic rod of say length L and if I move it with velocity V? So we know that in this case the induced EMF is the induced EMF is BVL. What is B? Magnetic field, intensity of magnetic field. B is the speed and L is length. Now what will happen if I change the situation slightly? Suppose if I have the same magnetic field, but now the way I turn the rod, the way I move the rod is changed. What change I am making? So now I will move the rod in such a way that its one end is fixed and the other end is allowed to move. So if the rod is initially like this, suppose I fix this end is fixed, and then you can turn it. See, you can turn it, and then if you turn it, you will be able to bring it here. So here also, I am giving velocity, I am giving some speed to the rod, but now the difference is when it is taken from situation 1 to situation 2, I am moving conducting rod in magnetic field, but I will not be able to use this formula BVL. L is fixed, B is fixed, but V is not fixed. Why? Because if you take this much length of the rod, say dr length of the rod, if you take, how much distance it is covering? This much distance it is covering, so it will have some velocity. Now go to another part. Suppose if I choose this much length, say dr of the rod, it will travel this much distance, so speed of this part of the rod will be more. And what if you take this part of the rod? Now you will see that speed of this dr, this much dr, will even be more. So velocity of this part, velocity of second part, velocity of first part, these three velocities are not same, and hence V is changing. And what do we do when one parameter is continuously changing? So what is the way out? Whenever you have some changing parameter, what you should do is integration, and that is the problem here also. Say if you take different parts of rod, if you take this part of rod, speed will be different. If you take this part of rod, speed is different. If you take this part of rod, speed is different, and hence epsilon is equal to BVL is not the formula we can use directly. So what we do is, instead of using epsilon is equal to BVL, I will take epsilon is equal to integration d epsilon. What is d epsilon? D epsilon is the EMF for the small part. I'll choose small region. I'll find out EMF of the small region and then I'll integrate. Which small region I'm taking? So I'll say that at r distance, say at r distance, I'm choosing some length dr and EMF of this dr is d epsilon. So what is d epsilon? D epsilon is b v d r. Okay. Once again, what is dr? Small part of rod. What is v? Velocity of that small part. Now that will create a bit of problem because we are given rotational speed, but we can always write it as v is equal to r omega. In 11th standard, you must have studied v is equal to r omega. So I will write v to be r omega dr. Okay, this is EMF produced in small length of the rod, and then I can say that epsilon is integration d epsilon, that is integration b omega r dr, that is integration, sorry, that is b omega. B is magnetic field constant, omega angular speed constant, r dr. We have to integrate from center to periphery, so center to capital R, and then it is b omega r square by 2, 0 to r, and then you will get epsilon to be b omega r square by 2. So this is the EMF induced in the moving rotating rod. Now let us see if we have all the data available. See, in first line we are given length of the rod, that is radius of the rod 1 meter, and angular frequency is 50 revolution per second. So it will be 2 pi into 50 radian per second. Omega is given. Magnetic field is also given 1 Tesla. So B is 1 Tesla. So you can substitute all the values and you can find out EMF between two rods. So that is all about 6th problem. Thank you.